let's talk about something else first. We want to create two groups of points, and in the proper order. If you've seen my previous video, you might jump into quickly into the conclusion that you need an array. When I say ordered, when I say list, more often than not, you need array. Array. You need an array, and you will need not one but two array, because you could use one array and have at index 0, 0 the first vertex, 1 second, 2, and at index 1, 0, 2. The thing I don't like in this kind of situation is that you will have to keep track of the maximum height. Here you have the width, and here you have the height. You will have to keep track of the maximum height, and it will only represent the number of vertices in one of the two sets. So you will be able to use, or you will have to keep track of how many vertices you have in each set. It's just a pain. I will use two different arrays, but I don't mean I will use two different array objects. I will just use two instances of the split list array. I will use two instances. During my algorithm, I will first destroy any instances I already have. I won't make them global. Don't know if it will hinder my algorithm, but I don't need them to be global. It's temporary. It's a temporary list of vertices. Here I will create two lists, and to identify which is which, I will create an instance variable I will name side. And the same way, I will create two constant to be able to use it. Side A and side B. You'll see we'll use them shortly. So I will create two arrays. Yeah, I will create them like that. Create array, split list. Don't need to do anything here. I will set the value side to side A, and here side B. So I have two independent array, and I will set their size to hold a list of vertices. They need to have in the width coordinate the index of the vertices, and in height the position of the vertices. So in height you will have two. For each vertices you will have two values, the x and y. And in width I will empty the array, so I will set to 0. Alright, so here we have two empty arrays which can hold two values in their y in their height and one value in their z. I don't need the z-axis. Alright, we have our groups. We can tear them apart. That's very important. We have our line equation, or we will have them once we will put the proper things in here. And then we can start going through all the nodes. So for each node, we have tons of stuff to do here. First, we have the situation where the node is exactly what has been picked here. So we will have node equal node index equal node 0. We'll have the situation where node index equals node 1, and to be sure I will change that, and for each ordered by self, I don't think I can use self here, by node dot index. Can I use self index? I don't think. No, not index. So here we'll go through all the nodes in the proper order, and then we will check tons of stuff. First, going by the proper index will help you to build the list in the proper order. If you start from here, let's say we have this line, a new example, this line here. If you go through the nodes in the proper order, 7, 8, 9, we'll be able to gather each vertices. First this one, let's say A and B, A and B. First this one, okay, then the 2, then the 4, then, since it's in the splitting line, the 5, and then the 9. Let's continue in the proper order. 5, the 6 will go here, the 8 will go here, and the 9. Okay, I did a mistake. Let's start over. 4, 5, 6, 7, 8, 9. Okay, this one now. We start with 0 on A and B. A, B. First 0 will be on the 2 list, that's where I did a mistake just now. Then 2 will be on B, 4 will be on B, 5 will be on the 2, then 6, then 8. And by going through the vertices, checking if they are on the splitting line, in this case we put them on both. If they are underneath, we put them on B, and if they are over, we put them on A. And we'll do that in one swift loop. Alright, we have the loop. We check if index is, it's the case where nodes are on the splitting line. In this case, we push them, push back. Yes, do that like that. I don't think I did it like that before, but I'll prefer this situation. So I'll push first, not index like that. I don't know. Last time I did that, I actually pushed the coordinates directly. Yeah, it will be more straightforward. You just need to do push node X, and then do something which might look a little bit weird. Set at XY self.width -1 and 1 and node.y. Okay, I think it needs some explanation. First I will create another constant just to represent x and y in the array to be on the clear side. X will be on the 0 index and y will be on the 1 index for the y. Yeah, for the y of the array. That's the kind of part where it gets a little bit harder to understand. It's the y index of the array, but you hold in this y index whether if the y index is equal to 0 will be the x, and it's equal to 1 it will be the y of the point you want to store. But here we use a mix of push and value, and that needs a little bit of explanation. I have an array which have at first which have 0 values, so it's a flat array, but have a height of 2. So I say for the sake of explanation, I say the x will be here and the y is here. So you have a y height of 2. It's a little bit I don't like to say it like that because I'm describing height in the horizontal way. So I think you are not misled by this. For now, I have the important thing is that I have a width of 0. So basically my array is totally flat. When I will push a value, it will push the value like that. It will extend the array and push the value of node x like that, x at index 0 and 1. And here will be index 0. It will push the same value. Will it? No, since I said it would do that if I had said, I think. Alright, I don't remember exactly, but that's not really important because whether or not it does that, I know at least that it does that. That will need investigation. I won't do that now. XY. So when I push the first value, I know it will at least do that, and here I don't really know, but it will do that. That's why on the second action I set this value to y, and I named the x underscore and the y constants to be 0 and 1, because this way I could name basically the axis, not the axis but the index of the y-axis. So each time you want to get the x, you can use this instead of this, which tells a little bit more about. So yeah, we will push. When we will push the second one, it will do that, and it will do a new axis here, and then we will add y here. So we'll push the x back when the array is totally flat. The back is just the beginning, and then the second back, the third back, that's what means the back here. I push the x here, and then I add the y in the y index. And for the current position of the last inserted node is the width of the array minus 1. Here you will have the width will be equal to 1, the index to 0, but the width will be equal to 1. So to have the index, you just have to do a minus 1. Alright, I will go back to the loop one more time when we will have finished it. Here it will be exactly the same thing. So to be a little bit more concise, you can do a or block. Okay. Now if it's something else, what could it be? It could be either a midpoint or not a midpoint. I'm not sure if that thing works. I think that thing works. If this, okay, that thing will work. So if it's not a node on the splitting line, it's something else. It's either a midpoint not in the splitting line or a vertex node. And I only need a vertex node. We only need vertex node. Remember, I totally discard every midpoint which aren't on the splitting line. If you split here, there will be no midpoint, just vertex points. Alright, so how do we tell apart vertex point and midpoint? Simple, I told you earlier, it's the modulo. So you just have to do node compare instance variable index. Alright, you can't do that like that. You need to do an operation with the index itself. So it will be node.index modulo 2 equals 0, and you are in good shape. Here you can use a system expression because the for each does the picking at first. If you were in the position where there wasn't a for each and you needed to know if something was even or not in the node, you would have to place a for each to be able to do that and keep the picking feature on. Anyway, yes, basically this kind of thing, just to add something else here, doing that is exactly the same as doing, let's see, I'm still on my stylus, I just doing for each node, and not that, but it's the same as doing node.index equal node 1. This one and this one is equivalent. Really. That's internally what this thing does is equivalent to that. It's not exactly the same, but it's really equivalent. The real difference is that here, no, I won't talk about the real difference because it's irrelevant for now. But it do exactly the same. It will if I do it will achieve the same thing. I could do to mimic this one. I could do that. I could do exactly that. It would achieve the same thing. Anyway, moving on. So yeah, if it's not a splitting node, you only filter the vertices, and then you will have to know you will do something like that, and I will write the function afterward. Which side equal side A, you will pick the proper split list. By the way, here it should add the node, and we'll check that, but it should add the node on both lists at the same time because they all picked here. But here we will only pick the side A list. Side A, and you will do the same thing here. Else, if it's not on side A, it's on side B, you will pick the side B, say side B, and add the vertices, and basically it's finished. We have all our list. Really, we don't need anything more than that. Except there's always an exception. In that case, vertical row, you will have to use another which side algorithm, which is far simpler. You will have to know another. Let's see. Do I continue or do I not continue with this version? Yeah. I will go through here first. So for each node, we first check if the node is either the first or the second splitting point we choose. If it is, we will add its coordinates on both lists, just by doing that, because they will both be picked. Else, if this event doesn't trigger, you check this event, and if the node, the index of the current node in the for each is even, it's a vertex node, you check the side according to the line, so it will probably be the function will probably look like that. You will give it the line, the x position of the node, and you will be able to the x on y position, and you will be able to know if the node is on top, on the bottom of the line. This parameter will give you is a way of giving the information of the line to the function, and this one is the information of the point. And the function will spit out in which side your point is according to the line. So it's on side A, you will push it on the side A split list. If it's not on side A, it's on side B, and you will push the line on the other list. And thanks to this loop, we will have all groups in a proper order. Okay, here it's good. Now let's see. Yeah, I will add the little special case of a vertical line. If it's a vertical line, this and this don't change yet. This doesn't change, and this doesn't change here, but it changed here. So we have to split our system into two possible cases. I will copy this one here, and here it will be an else. So let's handle the vertical line. If it's a vertical line, we want to keep, let's see, if it's a vertical line, drawing, alright, I will draw it, yeah, vertical and vertical from here. Okay, we have a vertical line, and what is the difference between this point here and this point here? How can we tell them apart? It's really simpler than the weird line thing. Basically, you will have the x, let's stay on the coordinate system here. You will have the x here, and everything who has an x greater will be on this side. Everything that has an x lower will be on this side. It's as simple as that. So you need to keep the x position. You could use x1 or x0, but I prefer having the value itself. It's we know what we are. If you start to mixing x0, x1, you don't really know what you. At some point, you start to add a kind of mixing of different meaning in a way. So I prefer, even if it's kind of redundant in the value, I prefer have something that is equivalent to that, which means this describes any line, these two values, and this one describes a vertical line. I can say any vertical line, and this way I would be able to use it here and do another kind of which side function to stay on the same kind of look of the code, which vertical side, and I will exactly do the same thing here and here. Oh, it's weird. Special keys. I think I did something really wrong if it's not vertical. Vertical to false. If it's not vertical, you use the any kind of line kind of algorithm, and if it's vertical, here special case is vertical. If vertical, you use this special case. All right. Okay. Else. Where did I put that? Alright, let's use that here. Any line equation. Okay. The equation of a vertical line is just simply the same way you had y equal ax plus b. For a vertical line, it's x equal k. K being, as b is a constant, k is another constant, which will tell which of these vertical lines we are talking about. Okay, they all have a different k. That's the only thing that tells them apart. And you can notice you can't know with this equation where the y of a point in the line. There's no correspondence because there are infinite points in the x position. Anyway, which vertical? So we need to write now. We need to write two other functions. Which side and which vertical side. The which side, as I said here, will take 4 parameters. Which side 4 parameters. Let's say simply an x and a y, and the which vertical line is far simpler. You get x0 x no, you get only the x of the point you are currently the node you are currently checking, and the x line of the line you are currently checking the node on. Okay, so here we have our algorithm. We'll write the complicated function here. You will see it will be as complicated as one formula, and then we are just short one thing. I think it's okay. Yeah, it's okay.